I brought it because I had stuff in it, but like.
This girl. sorry for late. So hi, howdy. Okay, so today, there is some echo. Give me a second. Uh, ah, ah, okay. So yeah, now echo is done. So okay, today I just found that my last lecture note was not updated in the OneNote. So I don't know why, but I will definitely fix it today. And one announcement is that, yeah, video take-home quiz due date is just the midnight of today. So please upload it before then. And I saw some of your videos and those are very interesting for me because actually I think that some problems are very difficult for you to solve. So I'm not expecting you to give me an answer, but a lot of you actually give me an exact answer. So I'm very satisfied with that. So thank you very much for solving this. So is it too difficult for you, or if there is someone who already did it? Mm-hmm. You make it so today is not. It is enough for you to solve it, right? Mm-hmm. Yes, that's okay. Okay, great. Yeah. Other guys also agree with it. Good. Okay, so I will keep that Windows in the future pages. And okay, thank you for feedback. So okay, so what we did in the last time is about the numeric. Sorry. So the number of Hamilton circuits, where the number of Hamilton circuits in the complete graph with n vertices has n factorial Hamilton circuits. And if we didn't count the mirror image as a separate circuit, then it has n factorial over 2 Hamiltonian circuits. So we just divide 2 for the Hamiltonian circuit itself. And if the starting point is specified, then there are n minus 1 factorial Hamiltonian circuits in the complete graph. And again, if we just ignore the mirror image, then you can just divide it by 2. And because there are so many possible Hamiltonian passes, so one way we can think about get some not optimal but some better solution is to use the nearest neighbor algorithm. So here is nearest neighbor algorithm. Okay, yeah, zoom it. So nearest neighbor algorithm is just showing that first of all, starting the home city. So you need to choose one city where you start from, and then just visit the nearest city first and visit the other nearest city you didn't visit it. Then repeat until no other choices remain. Then you have some Hamiltonian path or Hamiltonian circuit. Yeah, in that case. So from some examples we did with, so we say that it shows that it is better, but it may not optimal for some cases, right? So okay, so to review that nearest neighbor method, just revisit this table example first. So one important aspect of in the RAS structure is that this table can be actually thought as a complete graph, right? So from this table, you can actually make some complete graph with vertex 8, or from the graph or complete graph, you can make a table where each row and column is the vertices, and the cells are just writing the cells are memorizing the distance between two cities, right? So this is the table. So in that case, what we did in the last time is just use the nearest neighbor algorithm to solve the traveling salesman problem starting after, right? So I'll give the answer after the class. But yes, so today we will deal with the below one for reviewing. So use the nearest neighbor algorithm to solve the TSP starting at bar noon, right? So bar noon is here. So starting at bar noon, the nearest city from Barnum is Casper, right? Because it only takes 7 miles from the Barnum. And from Casper, except Barnum, the nearest city from the Casper is Sleepy Hollow, because 128 is less than every other distances except Barnum, right? And from Sleepy Hollow, so here is Sleepy Hollow, except Casper and Barnum, the nearest city is Newcastle, right? Because Newcastle has only 2-digit distance, but other cities have 3-digit distance. And in the Newcastle, you can see that actually from Newcastle, except Barnum, Casper, Sleepy Hollow, and Newcastle itself, the nearest city is Pine Bluff, because Pine Bluff 217 is definitely less than 246 or 537 or 409, right? And from Pine Bluff, again, you can choose the nearest city, which is Laramie. So here, yeah, so it already have a 2-digit distance. And from Laramie, you can go to, you already visited Newcastle, Pine Bluff, and Casper Barnum. So there are only 2 choices there. So Rock Springs or Afton. But Rock Springs is much more, Afton is much more farther than the Rock Springs. So we need to go Rock Springs. And from Rock Springs, the only choice you can go is Afton. And from Afton, you need to go back to Barnum again, right? So here, your path starting at Barnum, Hamilton Circuit starting at Barnum is, first of all, from Barnum to Casper by traveling 7 miles, and from Casper to Sleepy Hollow, 128, and from Sleepy Hollow to Newcastle, 78 miles, and from Newcastle to Pine Bluffs, which takes 217 miles, and from Pine Bluffs to Laramie, which also takes the 89 miles, and from Laramie to 207, sorry, not 207, it's this distance. From Laramie to Rock Springs, yeah. 207, and from Rock Spring to Afton, 180, and go back to Barnum using 355 miles, right? So that's the last problem in this example, and there are some chat here. So, okay, great. All right. So, do you have any question on this example or on your neighbor algorithm? Is everybody good? So it's just choosing, just start at the starting point, which is given, and just choosing the nearest cities and near cities and near city again, where you didn't visit before, right? Then you are fine. So that's the one method called neighborhood nearest neighbor method. And we deal with the other method, which is called sorted edges algorithm. So sorted edge algorithm is we just arrange edges of the complete graph in order of increasing cost, right? So just, for example, in this 3.6, just arrange edges from the least distance to the largest distance, right? So first of all, the least distance edge in here is 2, where from Miami to Veracruz. So it is takes 2, and the next smallest distance is from Barbados to San Juan. So it is 3. Okay, I will just, yeah. And the next one is 4, which is Miami from Barbados. And next one is just, and next one is 6 from Veracruz to San Juan. And oh, sorry, I forgot to mention Miami to San Juan, which is 3.5. So it should be definitely shorter than the Miami to Barbados. So Miami to San Juan, 3.5, and Miami to Barbados, 4, and Veracruz to San Juan, 6, and lastly, Veracruz to Barbados, 8, right? So first of all, sorted edge algorithm takes the lowest cost edge. So for example, in this case, we need to take this M to BC. So we just take this edge first. And then just see the next lowest edge. So for example, in this case, we need to look this edge from Barbados to San Juan, which is 3, right? Then just think that if we just add this edge on our Bayesian choice, does it make some cycle? If your answer is no, then you can add this edge, right? Or if we also, you need to check that if we just add this edge on our chosen edges, does it make some vertex has 3 edges? And if your answer is no, then also you can choose these edges, right? So it satisfies the first condition that if we just add this edge from Barbados to San Juan, then no vertices has 3 edges. Also, there are no circuits here, so we can choose these edges in our choices. So we can just choose it. And next one is Miami to San Juan. And again, just do the same question. So if you add from Miami to San Juan, then does it make some vertex has 3 edges? No, right? Because Miami has only two edges if we add these edges. And also San Juan also has 2 edges, and Veracruz and Barbados has 1 edge, so it doesn't have such a problem. And also it doesn't make a circuit, right? Because this one is not a circuit, so we can choose Miami to San Juan from here. Then again, we can see the Miami to Barbados. And if we add my edge from Miami to Barbados, does it make some vertex has 3 edges? Yes, right? So for example, if we add this part, then this M, Miami has 3 edges, which is 1, 2, 3, right? So we cannot add this one, so just delete it, right? Again, for the next one, still do the same question. So if we add from Veracruz to San Juan, does it make some vertex has 3 edges? Yes, which vertex? San Juan, right? So San Juan has 3 edges. So again, we cannot take these edges. And lastly, just thinking about the edges from Veracruz to Barbados. And if we just add these edges, and you can have a circuit, but it is the circuit for whole graph, right? Not the circuit for one of them. And also all vertex has 2 edges only, right? So we can add this one. So, and this gives you a Hamiltonian path, a Hamiltonian circuit, which is starting M to San Juan to Barbados to Veracruz, right? and its cost is M to San 1 is 3.5, SJ to B is 3, B to BC 8, and again BC to M is 2, so it is 16.5, right? So the method we use right now is called sorted edges, right? So first of all, thinking about the smallest edges first and add it to my kind of, my backs. And just looking the other smallest edges. And if that edge does not cause any problem, for example, what I mean problem is that if this edge, if the candidate does not cause a vertex have 3 edges, or if the candidate does not close the circuit until the all vertices is not included, then we can just put that edges in my bag. Otherwise, we can just throw it away, right? So by this method, you can have a Hamilton circuit, right? Do you have any question on this method or this example? Is it all good? Okay, great. So, okay, then see the next one. So again, this is heuristic. So it may not be an optimal solution, right? So it is just, so maybe we can see some examples whether this one is not optimal solution. So for example, in this case, it is not optimal solution because in the previous example, I think that, yeah, in the previous chapters, we already shows that, oh, yeah, it was deleted. I don't want to delete it. Yes, so maybe, yeah, it is not deleted. Great. So we know that 15 hour is the optimal solution for this passage, right? But in the sorted edge algorithm, what we have is 16.5 hours, right? Yeah, what we have is 16.5 hours. So it is definitely greater than 15 hours, which is our optimal solution. So yeah, its solution may not optimal, right? Okay. So, okay, for practice, we can do the next example 3.7. So solve the following TSP using SE algorithm. So again, yeah, in this kind of case, edges are also very many, right? So there are 10 edges. So you don't need to write down all, just picking the smallest two number you can see. So in these numbers, the smallest one is 12, right? So just picking this CD first. And next smallest edges are 13. And definitely if you just add 13, no vertices are shared to the chosen edges. And also no vertices have three edges. And there are no circuits, so you can just add this one. Next. And next edge is 14, which is from B to C. And again, adding B to C doesn't cause a circuit or doesn't cause a vertex have 3 edges, so you can take it. And next smallest edge is from A to B, but you cannot choose A to B, right? Why? Yeah, because B is the problem, right? If we choose A to B, then B has 3 edges, right? So that's why we can just delete AB. And next smallest edge is 16, but in this case, 16 also not possible choices, right? Because it makes a circuit, but this circuit do not contain A, right? So we cannot choose this 16. Then next smallest edge is 17, which is AE, and it does not cause any circuit or it does not cause a vertex have 3 edges, so you can choose it. then the only possible way to make a circuit is just choosing AD, right? Because all other choices don't make up some problems, so you can choose AD. And so what we have from this sorted edge algorithm is A D C E A, and its length is 12 plus 14 plus 13 plus 17 plus 30, which is, this one is 30, this one is 30, this one is 26, so it is 86. And is the solution found is optimal? No, right? Because in the last time, we already showed that actually the surrounding this graph has the optimal solution, right? So definitely is no. Okay. Does it make sense? Do you have any question? Okay. Okay, yeah. Actually, that's what I also had a problem. So what she asked, what do you name? Sorry. What Catherine asked is that how can we suppose that which number is, corresponds to which edges, right? So in the next time I make it much more bigger, but in this case, usually if you just see the graph in your textbook, for example, if we have, looks like this kind of, complete graph with 6 vertex, and usually number is always put on the top of the edges, right? So for example, if you have 2, 3, 4, 4, 5, and these are all the numbers which are close to these edges, but this weight of this edge is just 2, because 2 is just directly top of this edge, and 5 is actually top of this edge, and 3 is top of this edge, and 4 is top of this edge, right? So by this way, you can actually distinguish it, but I promise that I make it much more bigger in next time. But thank you for pointing out. Great. Yes. Do you have any other question? Okay, then let's derivate the minimum cost spanning tree. So a connected graph that has no circuit is called a tree. Oh, yeah, Harry says that there was also an issue on the Haycom keys problem number 48. So is it the same issue what I mentioned right now? So is it too small to recognize it? So okay, so then I will explain.
Yes, it
which
was
one.
on problem number.
Could you
So
explain
like,
it?
would you like if we still solved it and we got it right for like what numbers we thought corresponded to what lines? If we did the math right, even if we got the.
Okay, so I will. Okay, so I will make it clear after this graph. So we'll have some time. So I will make it clear how can we figure out the ratio of edges in the number 48, right? Okay, thank you for questioning.
Thank you.
Okay, so let's go back to the minimum material. So in the minimum cost spanning tree, so a connected graph that has no circuit is called tree, and this is kind of this is kind of the similarity that if you're thinking about the tree, I'm not good at drawing, but yeah. If you're thinking about the tree, then it looks like this, and you can think that there are some roots, and there are some, you know, kind of edges, and there are some kind of branches or that, right? But usually if you see the tree, then no branches are actually circuit, right? So for example, if you're just thinking about the tree in the winter, which has no leaves, then those trees are looks like this, right? So it doesn't have some kind of circuit inside of their graph, right? So that's why we call a graph that has no circuit is a tree. And it is just a simple question. Then what is just a graph that has no circuit is named for? So the connected graph that has no circuit is called tree. Then what is just graph that has no circuit? It is nonsense question. So not technical nonsense. Does anyone has an answer? So connected graph is just something that all vertices are connected by some passes, right? So unconnected graph is looks like this. So if we're thinking about these two as the same, as the elements in the same graph, then those are, it is called unconnected graph, right? Because this part is not connected with this part, right? So if you see some graph may not be connected, but that has no circuit, then what you can call? Could you speak more? Path. A path is just some way to getting from one vertex to another vertex. So I think it is not applicable at this situation. Then what is the bunch of trees? Forest. That's the answer. Yeah, usually mathematicians use that a graph that has no circuit is called forest. So yes, maybe you can forest, sorry, because it has bunch of trees, right? So yeah, that's just simple method. And the connected graph and one spanning tree is a tree that has all vertices of the original graph, right? So if you have some graph with circuits, then you can actually take the bones of the graph. What I mean bone is that just some graph connecting every vertices, but with spares the smallest edges, right? So it is called a spanning tree. So maybe you can see there are some issues here. So I will mute someone. Okay, give me a second. Actually, there are some. Okay, great. Sorry, okay, sorry for waiting. Okay, so spanning tree is some kind of tree that connects all the vertices in the original graph, but it is still tree, right? So for example, from this graph, you can find spanning tree looks like D as a root and just add all the edges, right? So maybe one of the spanning tree you can see is this kind of graph. Or you can actually make it the other graph. So for example, maybe you just love the edge from A to B. So just choose A to B and just add one more edge, B to D and D to E and A to C. So you can have a tree looks like this, right? Looks like line. So this is also one of the spanning tree, and more and more spanning trees are possible to draw, right? Since it is not a upper division course, I didn't encourage you to find the number of spanning trees you can make from one graph. But if you have a time, then if you do it for me, then I will give you extra credit for that. But yeah, so actually, so there are a lot of spanning trees can be made from the graph. So for example, in the next one, just choose any edge you want. So for example, I just choose the edge DF and CD. And I also want to choose CE. But in that case, I cannot choose EF at this point because if I choose EF, then it makes a cycle, right? So in that, if I choose already 3 edges from DF, DC, CE, then we cannot choose EF. Instead, I can choose FG. Also, I can choose BC, and I can choose raster AG to connect all the vertices, right? So one of possible spanning tree looks like here, right? And maybe there are more spanning trees. Okay, let's deal with one more example. So one more example in here, again, you can choose just any edge you want. So I just randomly choose DE, and I just want to choose AD. Then maybe I can choose AB, but this edge, right? There are 2 edges from A to B, so you need to only choose 1 edges, right? To make a tree. Otherwise, if you choose 2 edges from A to B in the simultaneous tree, then it makes a cycle, right? So if you choose 1 edge from A to B, then you cannot choose the other edge, right? And vice versa, right? So, and maybe you can choose FB. Then at this point, we cannot choose FE because if we choose FE, then it makes a cycle. So instead of FE, I just want to choose DC, right? Then it gives us a tree such that containing every vertices but not have a cycle, right? Okay. Do you have any question on this? Is it good? So as you can see, finding spanning tree is not that difficult, right? But what we are interested in the business situation is finding minimal spanning tree. That's what we call. So minimal spanning tree is a spanning tree with the smallest possible rate, right? So since we want to optimize our moving from graph, so we want to find the minimal spanning tree which contains all the cities we can visit. And to find the minimum spanning tree of the graph, we use the Kruskal algorithm. And this Kruskal is just name of some mathematician in the 50 years ago. And this algorithm is very similar to sorted edge algorithm. So that's why we run sorted edge algorithm first. So again, just made a bag for you to put your edges on the bag, and we call it as an empty set, right? Because that bag is empty right now. Then, like sorted edge algorithm, pick the edge with the smallest weight first. So just doing with this example. So in the first graph, this with this weight, there are the smallest weight edge is just B to D. So just put B to D on your back first. And next, just if your back has only has elements less than n minus 1, where n is just number of edges. Number of vertices in the graph. So in this case, we have 5 vertices, so n is 5. So when your number of edges in your back, m is less than 4, then just pick an edge with the smallest weight. So for example, except 5, the smallest weight edge is just 7. Then check that whether adding your edge gives you a cycle or not. If it gives you a cycle, then just throw it away. Otherwise, you just put it in your bag, right? So it is just same as the sorted edge algorithm, but it is much more simpler because we do not check whether this edge create the vertex with 3 edges or not, right? So only check the one thing you need to check is that whether your chosen edge creates a cycle or not, right? So for in this example, AD doesn't create any cycle, right? So you can add it. And the next smallest edge is AB. But when you just AB on your back, then it creates a cycle ABD, which is triangle, right? So you cannot add AB. So just delete it. And the next one is, next smallest edge is DE, which is has a weight 10, and it doesn't create any cycles, so you can add it on your back. And the next smallest edge is AC, which also doesn't create any cycles, so you can put on your back. And then now your back has 4 elements, so it is full. So now you're done, right? So the minimum spanning tree in this case is BDE AC with this shape. So what is in the blank? Bless you. There are nothing in the blank, I think. So yeah, here, what I say is that you just repeat this process until the number of edges in your back is less than or equal to less than number of vertices, right? So that's what I said in this part. Does it answer your question, Harry? Okay, thank you. And in this case, the cost of the minimum spanning tree is just adding all weights on the edges. So here we know that these are 11 plus 7 plus 5 plus 10. So in this case, it is 11 plus 12 plus 10, which is 33, right? Okay. Do you have any question on this algorithm or this example? Is it good? And one advantage of this Kruskal algorithm is that it seems a heuristic, but it's not. Actually, it gives you the optimal solution for finding minimum spanning tree. So we cannot deal with how can we get it, but that's why we call it as a Kruskal algorithm, because Kruskal process shows that actually this algorithm gives you an optimal answer. So it is not a heuristic algorithm. It gives you optimal answer without finding all the possible minimum spanning trees using brute force, right? So it is not heuristic. Right? Okay, let's deal with one more example. So here again, it is almost the same as sorted edge algorithm. So choose the first edge with the smallest weight, which is GF, which has 2, and next smallest edge AB, and adding AB doesn't give you a cycle, so you can add AB. And next smallest edge is BC, and again BC doesn't give you a cycle, so add BC. And next smallest edge is CE, and also CE doesn't give you cycles, so you can add CE. And next one is EF, and again, EF doesn't give you any cycles, so you can add EF. And next smallest one is 10 CD, and CD also doesn't give you cycle, and CD. Then all other edges, for example, 11, 12, 13 gives you cycle, so you cannot add it. So the final answer is this. Three, 5, 7, 8, 10, 2. And the total cost of the minimum spanning tree is 2 plus 3 plus 5 plus 7 plus 8 plus 10, which is 17 plus 18, 35. Okay. Does it make sense, or do you have any question? Okay, right. Good. Okay, then let's deal with the critical path analysis. So to deal with the graph, we will deal with some kind of graph with arrow, right? So previously we just deal with graph with edges, but edge has no direction, right? But now we will just give them kind of direction like this arrow, right? So in the real world, people always use some direction to move from somewhere to somewhere, right? So if your graph has some direction, we call it as your digraph or directional graph. Directional graph or digraph is your list of vertices connected by arrows. So, and if you just simulate your tasks as your kind of direct graph. So for example, to take this class, yeah, so example of tasks as your digraph. So just take math 167 in the classroom. Then first of all, what you need to do is just go to this building, ISCB 205, and you can sit on the red dot chair. And next, you need to wait me because I need to give you a lecture. So wait the instructor. And participate the class. And after the end of the session, you need to go back to house or go back to house, right? So if you're thinking each one as a task, A, B, C, D, E, then you can just depict your task as A, B, C, D, E, right? So in this case, every task is just single element, right? But for example, for some reason, because, for example, maybe you have a text message from your family that about your to say hey, hello. Then maybe you can just move out to this room and just taking your phone from family or your friends, right? So in that case, maybe you can add some kind of jobs like the frame as talking with someone, or when you just seated on the chair, then maybe you can also put also you can sit with chair by using talking to your friend, right? So in the real world, the graph may be not this line, but there are some other jobs. For example, C prime also is needed. Or for example, if you need to take the quizzes, then you need to you must open your computers and put it visit the eCampus, right? So maybe the other jobs is needed to participate the class, right? So for example, maybe you need here you need to open your computer is also needed. 자, E prime, say, sorry. E prime. So all those things actually make some graphs difficult. So that's why we do some analysis on that graph to make the optimized move, right? So in this kind of graph, which depict path is as order, it's called order requirement diagram. So if the time of the complete task on the diagram is shown, then it is called a weighted diagram, right? So these numbers, so for example, yeah, from your house to IICB, you can take 5 minutes to do it. And from this classroom to sit on some chair, you can take 1 minute maybe. And wait instructor is maybe 10 minutes. And participating class is just 75 minutes. And go back to your house is just taking 5 minutes. So you can put it those kind of weights on the graph, right? 5, 1, 10, 75, and something like that. So those number of time or those numbers in the arrow is called weight. In that case, we call it as a weighted graph, right? So it is very similar to just graph. So it is just weighted graph with arrows, not on edges, right? Go. Do you have any question before going further? Okay, so let's do some examples. So suppose that the first task T1 takes 4 minutes and the second task T2 takes 6 minutes, and assume that T2 cannot be started until T1 is done, then you can see that actually this is made as T1 to T2, right? So it is just the same as you cannot sit on the red dot chair unless you be in this classroom, right? You must be in the classroom to sit on the chair, right? So the task T2, in this case, sitting on ladder chair, should be cannot be started until you are in the classroom, right? So in that case, we represent it as a diagram with an arrow, and an independent task is one that can be done independently of any other task, right? So it is, for example, it is kind of talking with someone else using your phone during the class, right? It can be just independently doing, right? So in that case, we can just put it on the other edges and there are no relationship between other tasks with arrows, right? So we can put it on this kind of T3 in this example. shown independent because there are no arrows between other tasks, right? Okay. Then let's deal with some examples. So example 5.4 shows that break down the first receipt below into a series of tasks. Show this task in a weighted order requirement diagram. So yeah, we have some ingredients. And first of all, you need to slice the onion and chicken into the strips, right? And it will take 2 minutes and 5 minutes respectively. So task 1 is slice the onion. And task 2 is chicken, slice the chicken. And it takes 2 minutes for task 1 and takes 5 minutes for task 2. And this can be independent, right? You don't need to slice chicken first to slice onion, but you don't need to slice the onion first to slice chicken, right? So these are so independent. So you can just put it as, okay. 2 minutes. So 2 with T1 and 5 with T2, right? And next job is cook chicken 10 minutes. So next one is cook chicken 10 minutes. And add onions and cook more for 5 more minutes, right? So first of all, so this 4 is add onions. So maybe just assume that adding onion just take 1 minute. And the 5 is cook more on 5 minutes. Then here, T3 is cook chicken, which take 10 minutes. Sorry. But you cannot cook chicken until you slice the chicken, right? So cook chicken is independent. And then again, oh, I think I need to throw it in here. Sorry. Right? And next, you need to add onion, which takes 1 minute. But you cannot add onion until you slice the onions, right? So T1, T4 is dependent to T1. And the next job is T5, cook 5 minutes more. So this is T5. And we need to cook 5 minutes more after adding onions. So T5 is dependent on T4. So that's why I choose this graph. So is it good, everybody, or do you have any question before going further? So what we do right now is just turning this recipe or turning some task orders into a diagram, right? With some number of times. And next one is add seasoning. And yeah, T6 is add seasoning. It takes 1 minute. And T7 is chop tomato, which takes 2 minutes. And T8 is mixing with cilantro, which takes 1 minute. And T9 is warm tortilla. And T10 is serve it. serving it in 5 minutes. So in that case, first of all, you can add seasoning after you cook the chicken. So seasoning T6 is depends on the T5, which is just cooking the chicken. And chopped tomato can be made independently on the chickens, right? So you can actually make T7 as 2 minutes in here. And also mixing with cilantro is only depends on the chopping tomato, right? So T8 is also dependent on T7 only. So and mixing with cilantro, it takes only 1 minute. And you can also warm your tortillas without, depending on other jobs, right? So you can write down the T9 warm tortilla, 1 minute as T9. And to serve this, you need to put together on serving all of these, right? So the last job is T10, and it defines all other works you did, right? So the final diagram looks like this. Does it make sense? Good. Okay. Yeah, I just guesstimate that adding onions would only take 1 minute. So yes, because I didn't add it in the recipe, but yeah, I just guesstimated. Thank you. Okay, so in the exams or in some homeworks, you need to turn the recipes into the diagram or turn diagram into recipes or vice versa, right? So this is one of the example. And lastly, we want to deal with some concept called critical path. So critical path on the diagram is the longest path in the diagram. So it is just nothing but some path in the diagram. We hit the longest ways, right? And it determines the earliest completion time. So the earliest completion time is just possible time for completion for all the tasks that making up job into diagram. So what I mean is that, so let's see this example again. Yeah. So in this example, even if you make up for these two jobs, T7, T8, T9, so plus for chopping tomato and mixing cilantro and warm tortillas. But if you didn't make a job on this chapter from cooking onion, chickens, and something else, then you cannot make it into a whole task, right? So whether, so this job from cooking chicken is definitely the longest job you need to do for completing the tasks, right? So even if you can earn some times, or even if you can some investment to chopping tomatoes or mixing cilantro, so that if you decrease your cost on those jobs, you cannot decrease the cost of the whole job, right? Whole job's cost is still depends on the longest path. So that's why we call it as a critical path. To make decrease all of the tasks at once, you need to decrease your critical path first. Otherwise, even if you have some improvement on other jobs, but it is not in the critical path, then it doesn't decrease your job time for completing some task, right? So that's why we are focusing on critical path. Does it make sense? Okay, and there are some questions from Taylor that can you go back to the definition of independent? Okay, sorry. So independent task is the one task that can be done independently. And it was shown in the graph that no arrows are put on that, no arrows are connected for independent task, right? So dependent task is some task which is from some, which has some arrows from other ones, but independent task is just no task. Yeah, you can do it. right? So for example, in this diagram, T3 is the independent task, right? Does it make sense, Taylor? Okay, great. So let's find the critical path for making fajitas. So I also already said that, but let's deal with it why this one is the critical path. Okay, so first of all, yeah, if you just add all the job time for doing this, then this path gives you 5 plus 10 plus 1 plus 5 plus 1 plus 5, which is 15, 12, 27 minutes, right? But if you just draw the path from T1 to doing this path, for example, this red path, this yellow path gives you 2 plus 1 plus 5 plus 1 plus 5, which is 14, still less than 27. And if you just draw this path, T7, T8, T10, this blue path gives you 2 plus 1 plus 5, which is 8 minutes. And, oh, sorry, I need to put another color. If you see this, oh, sorry. See this Viola path, then this Viola path only takes 1 plus 5, 6 minutes, right? So here, the longest path is this green one. So green one is the critical path of the making fajita, right? Do you have any question or does it make sense? Okay, great. Then let's deal with some other examples. So we can determine the critical path in the diagram below. So yeah, it seems a little bit, complicated, but you can figure it out using, just choosing all possible ones. So for example, to deal with all the jobs, the jobs with the greatest completion time is T7 first, right? So it has 12 minutes, and this T6 also 12 minutes, right? So maybe, and also the next one is T3, and the next one is 9, which is T2, and the next one is, sorry, 8, right? So you can figure it out that actually this path from T3 to T5 to T7 is 10 plus 8 plus 12, T3 to T7 gives you 30 minutes. And no other passes, for example, here we maybe 9. Here, if you change T3 as T2, then 10 is just decreased to 9, so it doesn't give you a critical path, the longest path. Or if you just change T5 into T6, then all you can do is just choosing T8 or T9 to have a path, but 7 is definitely less than 12, so it doesn't also give you any critical path. So by checking all other possibilities, you can see that actually this one, this diagonal one, gives you a critical path, right? Does it make sense? Or do you have any question? So the earliest possible time for completion of the task in the diagram is 30 minutes, right? Because even if you can implement on the task T6, it doesn't make you the step shorter, right? Because you need to complete this T3, T5, and T7, and it takes some time to do that, right? Okay. Do you have any question on this? Or do you have any other question? Great. Then I will just briefly mention about the quizzes. Oh, there are some questions from Katie that for our exams, do we need to know the definitions or just how to apply them? So yes, if you know how to apply them, especially for algorithms, if you know how to apply them, you are fine. But for some concepts like Hamiltonian circuit or Eulerian circuit or something like that, then you need to remember what the definition is. Not the exact word, but just meaning of the definition. And okay, give me a second. Now go to the eCampus and make clear about the number 18 or other numbers. Okay. Pages. Okay. Okay, so let's clear for the first one. So I think that 16 and 17 are just clear. And 48 right here, for example, I think that A is clear, right? Can you figure out the which edge rate is related to which edge? So for example, 18 is related to AB, and 56 is related to EB, and 69 is related to AC, and so on, right? But problematic one is the B. You cannot see. Okay, so give me a second. I will share it. Okay. Okay, sorry. Now can you see it? Yeah. Okay, great. So here 31 is definitely AB, but 59 is for AF, and BF is for 39, and BE is for 60 because 60 is just top of the edge, and 47 is from A to C, and 42 is for F to C, and BD is 8 is for BD, and DC is for 62, and EC is for 38, and so on, right? So I didn't take off the point if you just figure out this graph wrong, because I know that this is a little bit complicated. But in that case, you need to explain why you choose if you're applying this algorithm on the example is just fine, then you are okay, right? So don't worry too much about this. Yeah, AE is actually 28. Lainey, okay, yeah. 28 is for AE. 8 is for BD. Okay, so that's the number 48. So actually, I think that you're doing on the number A, and AD is 43, yes. So the problematic one is actually B. So there are lots of questions from students that how many Hamiltonian circuits would have to be examined to find the shortest route for part A by the Bluetooth method. So the questions, a common question from the students is that, should I count all the Hamiltonian circuits with mirror image, or should we just think mirror image as the same one with the other Hamiltonian circuits? And my answer is, actually, it's a part of the problem, right? So if you can make an argument such that if you only count mirror image as not the separate circuit, but you can still find the optimal one, then you didn't, yes, you can, you didn't want, you do not want to count all the Hamiltonian passes, all the Hamiltonian circuits, including mirror image, right? But if you didn't find such an argument, then maybe you need to calculate all the edges, all the Hamiltonian circuits in this problem. So it is also part of the problem. So I will give you an answer after the quiz. So yeah, that's what I mentioned for 48. Does it answer your question, Miriam? Okay, great. And do you have any other question for 48? Okay, then I will explain the other problems. So honestly, in my thought, 54 is the most easiest one among the problems if you can use some calculators properly. But yeah, but so it is just nothing but finding the number of possible Hamiltonian circuits in the complete graph of 20 vertices, right? And what is this? 20 factorial, right? Mm-hmm. And 20 factorial or 20 factorial, or if you can, actually, if you can solve the question from the 48 such that whether I need to count the or separated mirror image or not, then you can actually count it only half of the 20 factorial. So it is also part of the question. But anyway, if you can calculate 20 factorial and turn it into years using the 1 billion per second, then you're fine, right? So do you have more question on 54? Okay, and next one is 35A and B. And for B, I hope that for my grading easier, please for number B, use the schemes for license plate in Texas, right? I know what the license plate scheme on the Texas is, so please use it even if you're from other states. So that's what I want to mention. But 35 is just nothing but using the fundamental theorem of counting, right? That's what we learned from the last week. And number 24, actually this one seems very difficult, but one of the easiest thing you can solve if you know how to do it. So for example, the n dimension, this one asks you to find how can you find that every n-dimensional cube has a Hamiltonian circuit, right? So for example, the one cube is just an edge, right? And two cube is just from two edges connect each corresponding vertices. That's the two cube. And three cube is just from two cubes. Yeah. Okay, it doesn't give you better conditions. So okay, to make something looks like 3D, so just connect the corresponding edges, right? So that's the three-dimensional cube, and so on, right? So, for example, you can definitely find the Hamiltonian path for edge, right? Just going here and just go back to here, right? That's your circuit, but it's F. But in the two cube, you can also find the Hamiltonian circuit just going around, right? But when you're thinking how this going around is related to this Hamiltonian path in the one cube, then actually what you did is just delete this part of go back to one. So for example, you can just try to mimic the Hamiltonian circuit in the one cube. Just just follow this circuit so from here to here, but instead of going back, you can go below, right? Then again, you can do the just Hamiltonian circuit, but with the reverse order or its mirror image, and just go back using this path, right? So that you can have the Hamiltonian circuit. Then you can do the same thing on here. So here again, just pro with circuit, but after going to the, after go back to your original one, just go other way and just go other direction and go back to here to get one Hamiltonian circuit. Can you make it a generalized for the n dimensional circuit? Then if you can, then you are possible. Okay, so I think that that's the time. So I stopped here. Thank you for listening. And if you have any other question, please let me know. I have more time, so you can always have a question. Thank you very much. Yes, quiz grading scheme, as I mentioned in the announcement, so it is only 10 points and 5 points for your introduction, your name and your motivation, and 3 points for your logical flow logic, and 2 points for final answer. And I also announced that if you just do two programs, then I will refresh one of your lowest score in the quiz at the end of the semester. Yeah, that's my. Yes, you can. I can replace your first quiz on the website as a full credit. Great. Thank you very much, Romero. Okay. Is there any other question? Okay. If you have any question, please let me know by email. So I will just end the session. Okay. Thank you very much for taking this course. See you next week.